top of page 2 of your notes. And this is the symbolic or algebraic form of the function. Okay. In this example. And so the algebraic form of the function, f of x is equal to x squared over 3x plus 1. And we did the first three, right? We evaluated the function x equals -4. We found the reciprocal of the function and simplified it. And then we evaluated the function 1 over 3t, right, at x equals 1 over 3t, and simplified it. And now we'll evaluate function at x equals 2a, and simplify it. So f of 2a, right, you just put 2a in for x on the right-hand side. We have 2a squared over 3 times 2a plus 1. And now 2a squared.
Does the plus 1 need to be on the outside?
Thank you very much. I had a mental error. You're right, it's 3 times 2a plus 1. Thank you. So put 2a in for x and get 2a squared. Right, and then put 2a in x here, and that's 3 times 2a plus 1. So 2a squared, right, rules of exponents, is equal to 2 squared times a squared, which is 4a squared. And then you don't distribute the 3. This is equivalent to 3 times 2 times a. You only distribute if there's a plus and or a minus in there, right? If you're adding or subtracting terms. And we're not adding or subtracting terms inside parentheses, we're just multiplying. So this same is 3 times 2 times a, which is 6a. 6a plus 1. Okay?
Would you not divide the 4 and 6 by 2?
Ah. Who said that? Now, technically, and if you did, you're saying the numerator would be 2a squared, and the denominator would be
3a.
plus 1.
3a. You divide by 2.
What happens to the plus 1?
Stays the same.
Yeah. And here, let's review this, okay? So I have 4a squared over 6a plus 1, because I'm glad you brought that up, because this is the kind of thing I see a lot on exams, okay? Is, you know, people will have like x squared plus 3x plus 1, you know, over x squared plus 1, and they'll cancel out the x squareds. Can't do that. Fraction bars are like division symbols. Division does not undo addition. Okay. So if we divide top and bottom by 2, so in the numerator, we're dividing this product 4 times a squared by 2, and in the denominator, we're dividing a sum by 2. Okay. And division does not undo addition. Okay. And so 4a squared divided by 2, okay, looks like that, right? Because division, fraction bars are like division symbols. Division symbols are like fraction bars. And this here is 6A plus 1 over 2. So 4A squared divided by 2. 2 goes into 4 twice. You have 2A squared. 6A plus 1. You have to divide 6A by 2 and 1 by 2. Division does not undo addition. So this is 6A over 2 plus 1 over 2. You're adding these two terms, not multiplying. Up here we're multiplying, so we can just divide the 4 by 2. But here we're adding two terms, so each term gets divided by 2. Okay. Now, in this term here, this is 6 times A, so I can divide 6 by 2 and get 3. And I'm left with 3 times A, and then I got the plus 1/2. So it's not just dividing the 4 and the 6 by 2. Because this addition, you gotta divide the 1 by 2 as well. Okay. And I can prove that, and then we can also show this is true, okay, by just using a value of A. So let's use A equals 1, okay? If I put 1 in for A, I have 4 times 1 squared over 6 times 1 plus 1. And now you do the arithmetic in the numerator and arithmetic in the denominator. And 4 times 1 squared is 1. 1 times 4 is 4. The denominator multiplication for addition. 6 times 1 is 6, and 6 plus 1 is 7. So when A is equal to 1, this is equal to 4 sevenths. Now, if we could divide the 4 and the 6 by 2, and have 2A squared over 3A plus 1, right? Which you might suspect. When you put 1 in for A, you have 2 times 1 squared over 3 times 1 plus 1. 1 squared is 1. 1 times 2 is 2. The denominator is 3 times 1 is 3, and 3 plus 1 is 4. That's equal to 1/2. But 4 sevenths is the correct answer. And so if you just divide the 4 and 6 by 2, you actually create a different number. Okay. So that's why I keep saying, okay, division does not undo. Division does not undo addition. Okay. I see this on exams a lot, and it's important to understand that. Okay. Division does not undo addition or subtraction. Okay. It only undoes multiplication. Yes, ma'am.
Isn't that supposed to still be 1/2?
Where? Here? Yeah, I'm showing,
Oh.
what I'm showing is you can't just divide the 4 and the 6 by 2, right? Because when you put in a number for A, you get the wrong result. Okay. This is the correct result. Okay. When I put 1 in for A, okay, I get this fraction is equal to 4/7. Well, if I just do as was suggested and just divide the 4 and the 6 by 2, and then when I put 1 in for A, I don't get 4/7, I get 1/2. 1/2 is wrong. Okay. All right. So we will review these kinds of things as much as we can this semester. All right. Any other questions? All right, so you flip over to page 3. We're going to talk about finding the domain of a function. So in section 1.5, when we were manipulating and simplifying algebraic expressions, right? I would ask, for what values of x does this simplification, when does the expression not equal the simplification? Right, for what values of x? And that was to prepare you for the idea of the domain of a function. Okay? All right. So the basic idea in finding the domain of a function. So if we have the function f of x, and we want to know what are all the real numbers we can put in for x, and the value of the function will be a real number. Okay? That's the domain. All the real numbers we can put in for x, and the value of the function is a real number. Okay? So what we basically do is we start with the set of all real numbers. Minus infinity to infinity. Right? And some of you in high school, right, you might use that symbol to represent all real numbers. Right? It's every number on the real number line. And so and another way to write all real numbers is in inequality notation. Right? All three of these are for the variable x, right? The input variable x. And so what we basically assume is that the domain is all real numbers, and then we look for values of x that don't work. We look for restrictions on the variable x. Okay? And then using those restrictions, right, we can define the domain, okay, for a particular function. And so 2 cases that you have to be concerned about is division by 0 and taking the square root of a negative number. Because the square root of a negative number is not a real number. Okay? So 5, right? Fraction bars are like division symbols, right? This is 5 divided by 0, right? And any real number divided by 0 is undefined. You can never divide by 0. Okay. On the other hand, 0 divided by any non-zero real number is 0. That's defined. Okay. But you can't divide by 0. Right? And similarly, 0 divided by 0 is not 1 or 0. It's undefined. You can never divide by 0 mathematics. Okay. So in finding the domain of a function, we got to concern ourselves with values of x that make the denominator in the function equal to 0. And those values of x, right, are not in the domain. Okay. The square root of a negative number is not a real number, right? So square root of 25, right, that's a positive number. Right, that's equal to 5. Right, you know that's a real number. But square root minus 8, that's not a real number, right? That's an imaginary number. And we'll be doing some work with imaginary numbers this semester. Right? And the famous one is, right, square root of minus 1. What'd you call that number in high school? What letter did you give it? Yeah, I. So that's the famous one. You never take the square root of a negative number. All right. So let's demonstrate how to find the domain of a function. So in the first one, we have g of x is equal to 2x over x squared minus 5x plus 6. Okay. Now you notice there's no square roots in this, right, involving the variable x. But we have a quotient, and we have a quotient with the variable x in the denominator. So we have to concern ourselves with numbers that we can put in for x in the denominator, and the denominator will equal 0. Okay. Those numbers that make the denominator equal to 0 are not in the domain of this function. Okay. The only numbers that are in the domain of this function are the numbers we can put in for x, and the value of the function is a real number. Okay. Now, the number 0 is in the domain of this function. X equals 0 is in the domain, because when I put in 0 in for x, I have 2 times 0 over 0 squared minus 5 times 0 plus 6. Numerator 2 times 0 is 0. The denominator, using PEMDAS, right? The exponentiation, the multiplication, and the addition, subtraction, right? You end up, this is just equal to 6 in the denominator. And 0 divided by 6 is equal to 0. And 0 is a real number. Okay? So x equals 0 is in the domain of g of x. Okay. You can't divide by 0. You can take 0 and divide it by a non-zero number, but you can't divide by 0. So, basically, listen, the domain is all real numbers, except for those values of x that make the denominator equal to 0. So one way to express the domain for this function is with inequality notation. The denominator, x squared minus 5x plus 6, can't equal 0. You can equal 1, you can equal 10, you can equal minus 80, it just can't equal 0. Because if this denominator equals 0, we're dividing by 0, and division by 0 is undefined. Okay. Well, this is a quadratic on the left. We can factor it. And when we factor it, we get x minus 2 times x minus 3. And that can't equal 0. So that means x minus 2 can equal 0, and x minus 3 can equal 0. Okay? Because if either of those factors equal 0, then the product is equal to 0. But it can't equal 0. So x minus 2 can't equal 0, and x minus 3 can't equal 0. which means when I solve for x can't equal 2, and x can't equal 3. If x is equal to 2 or 3, this denominator up here is equal to 0. Okay. So the domain is all real numbers except 2 and 3. So let's graph the domain. Remember, the domain applies to the variable x, the input variable. Okay. So here is 2. Here is 3 on the real number line. Open circles on 2 and 3 because they're not in the domain. Every other number is in the domain. So we shade all the real numbers to the left of 2, all the real numbers between 2 and 3, and all the real numbers to the right of 3. That's the graph of the domain. Okay? That's the graph of all of the numbers you can put in for x on the right-hand side, and the value of the function is a real number. Well, in interval notation, right? Because ultimately you got to write the domain in interval notation. So this first interval for all real numbers less than 2, how do we write that? Parentheses, minus infinity, comma 2, right parentheses. For all the real numbers greater than 2 and less than 3, how we write that? Parentheses, 2, comma 3, right parentheses. And for all real numbers greater than 3, how do we write that? Parentheses, 3, comma, plus infinity. This is the domain in interval notation. Those are all the numbers you can put in for x and g of x, and the value of the function is defined. Okay. So let me emphasize why 2 and 3 are not in the domain. If we try to evaluate the function x equals 2, when I put 2 in for x on the right-hand side, 2 times 2 over 2 squared minus 5 times 2 plus 6. The numerator is equal to 4. And the denominator, doing PEMDAS, is equal to 0. And 4 divided by 0 is undefined. So the function is undefined at x equals 2. That's why 2 is not in the domain. And similarly for x equals 3, put in 3 in the right-hand side of the function. The numerator is equal to 6. And applying PEMDAS to the denominator, you get 0 again. And 6 divided by 0 is undefined. So the function is undefined if x is equal to 2 or if x is equal to 3. That's why those two numbers are not in the domain. Okay. Any questions on that, ladies and gentlemen? Okay. All right, let's take a look at one in finding the domain involving a radical. So we have f of x is equal to the square root 3x minus 2 over x plus 5. So we have the square root of that quotient, okay? Now remember, the square root of a negative number is not a real number, right? So, square root minus 8, not a real number. Right? Square root of any negative number is not a real number. Square root of 0 is equal to 0. 0 is a real number. And square root of 17, 17 is a positive number. The square root of any positive number is a real number, right? So square root of 0, square root of any positive number is a real number, okay? So we have to concern ourselves with values of x that make what's under the radical here. This is called the radicand, okay? What's under the radical is called the radicand. And so we have to concern ourselves with those values of x that make the radicand negative, right? Less than 0. Or another way to put it, concern ourselves with those values of x that make the radicand equal to 0 or positive, okay? Greater than 0. So one way to express the domain in inequality notation is to say that the radicand has to be equal to 0 or greater than 0. The radicand, what's under the radical, has to be greater than 0, right? Has to be positive or equal to 0. If it's less than 0, then the function's undefined. Okay. Well, how do we find the values of x, okay, that make the left-hand side greater than or equal to 0? Okay. This is exam 1 material. I want to emphasize, math is cumulative. You thought everything you saw in exam 1 you'll never see again this semester? Ha! You'll be seeing it periodically throughout the semester. This is a rational inequality. We know how to solve those, right? This is section 1.1 material. You had a rational inequality on the exam you had to solve. Okay? We're in test point. This is test point method material. Okay? So we got to find all the real numbers we can put in for x that satisfy this inequality. Okay? You remember how to do that? Right? Exam was just yesterday. Well, step number 1, make sure you got 0 on the right hand side, which we do, which we require because we're trying to find the domain of this function. Step number 2, set the numerator equal to 0, set the denominator equal to 0, and solve for x. And I don't want to, but looking at other men's armpits, you know.
Oh, sorry about that.
Yeah. So I don't want to. I know you want to be comfortable, but it's hard to look at it from from up here. All right. So step number 1, make sure 0 is on one side. Next step, set the numerator equal to 0, set the denominator equal to 0, and use those, and solve for x, and use those values of x to divide up the real number line and intervals, right? So we have 3x minus 2 is equal to 0. X plus 5 is equal to 0. And when you solve this equation for x, get x is equal to 2/3. We solve that equation for x to get x is equal to minus 5. Okay. So here's the real number line from the variable x. So here's minus 5. Here's 2/3. Now, minus 5 is not in the domain. It makes this left-hand side here undefined, right? You put in minus 5 in for x in the denominator. You have minus 5 plus 5 is 0. You're dividing by 0. Division by 0 is undefined. So minus 5 is not in the domain. It's an open circle. 2/3, on the other hand, you put 2/3 in for x. The denominator equals 5 2/3, right? Which is not 0. But the numerator, you put 2/3 in for x, the numerator equals 0. So you have 0 divided by 5 2/3. 0 divided by 5 2/3 is 0. And 0 is equal to 0, right? Our inequality symbol is greater than or equal to 0. So 2/3 works in satisfying our inequality. So we put a closed circle on 2/3. And now we have these three intervals we gotta do the test point method with. Okay. Yes, sir.
Can you explain one more time why 2/3 has a closed circle?
So if we put 2/3 in for x here. On the left-hand side of the inequality, we have 3 times 2/3 minus 2 over 2/3 plus 5. Okay? 3 times 2/3, 3's cancel. And we're left with 2 minus 2. And 2 minus 2 is 0. And 0 divided by, this is 5 2/3. And so 0 divided by 5 2/3 is 0, and 0 is a real number. Okay. So 2/3 works because our inequality symbol is greater than or equal to 0. Okay. The left-hand side can equal 0. All right. So now we got to do the test point method. Okay. So we got to plug in the 3x minus 2 over x plus 5 for different values of x. So minus 6 is to the left of negative 5. So if I put in minus 6 in for x, I have 3 times minus 6 minus 2 over minus 6 plus 5. And that turns out to be negative 18 minus negative 20 over negative 1, which is equal to 20. That's positive. So any 20 is a positive number. So any number less than negative 5 put in for x over here makes the left-hand side greater than 0. So those numbers work. So those numbers are in our domain for this function. In the middle interval, okay, 0 is in the middle interval. So when I put 0 in for x down here, I have 3 times 0 minus 2 over 0 plus 5. When I do the order of operations, I get minus 2 in the numerator, 5 in the denominator. Well, minus 2/5 is less than 0. And the left-hand side value left has to be greater than 0. So none of those numbers work in our inequality over here. And then lastly, in the third interval, 1 is greater than 2/3. So when I put 1 in for x down here, I have 3 times 1 minus 2 over 1 plus 5, which is equal to 1/6. And 1/6 is a positive number. So any number greater than 2/3, put in for x over here, the value of the left-hand side will be greater than 0. So those numbers work. So the numbers in our domain of our function here are all the real numbers less than minus 5 or greater than or equal to 2/3. So the domain is all real numbers less than minus 5. Right? These are the numbers we can put in for x up here, our original function. Or greater than or equal to 2/3. Those are the numbers we can put in for x. So 0 over here, right? 0 didn't work because when you put in 0 in for x, the radicand's equal to minus 2/5, and the square root of minus 2/5 is an imaginary number, not a real number. Okay. Any questions on that? Yeah. Okay. So I'll see you Friday.